Imagine this. When you enter your payment password on your phone, those seemingly random digits are actually building a strong digital fortress through encryption algorithms. But scientists warn that one day in the future, this fortress, something humanity takes great pride in, might be easily penetrated by quantum computers. They could crack in just minutes what would take traditional computers millions of years, slicing through it as effortlessly as a scalpel cutting paper. So what exactly is a quantum computer? And why is it so powerful? Today, let's take a journey into the quantum world, from qubits to quantum superposition, and uncover the real secrets behind quantum computing. First, let's start with the computers we're familiar with. In a classical computer, the smallest unit of information is the bit. A bit can only be one of two states, either 0 or 1. Like a switch, it's either on or off with no in between. For example, the text, images, and videos stored on your computer are all just massive sequences of 0 and 1. A quantum computer, on the other hand, is based on the quantum bit or qubit. Unlike a classical bit, a qubit follows the principle of quantum superposition, meaning it can be in a state of 0 and 1 at the same time. Imagine a spinning coin. It's not strictly heads or tails until it lands. It's a mix of both. This mixed state can be described mathematically as a probability amplitude, and only when measured does it collapse into a definite 0 or 1. In classical computing, power grows linearly with the number of bits. Add one bit and you just add one more state. The system can only handle one specific state at a time. Even with multi-core processors, it's still just dividing up the work across many single-state processors. For instance, if you want to brute force a 4-digit password, a classical computer must try each of the 16 possibilities, one by one. But with quantum computers, because of superposition, and qubits can represent 2 to the power of n states simultaneously, all possible combinations at once. So with just 4 qubits, you can explore all 16 possible password combinations in one go. This parallelism doesn't come from multiple cores, it's a natural feature of quantum states. That's why the power of quantum computing grows exponentially. Each additional qubit doubles the possible states the system can process. For example, 30 qubits can represent around 1 billion states, already beyond the reach of today's supercomputers. 50 qubits can represent a quadrillion states, enough to crush the limits of classical computing. Beyond sheer computing power, the greatest advantage of quantum computers over classical ones lies in efficiency when solving complex problems. A classical computer, when tackling problems like code breaking or molecular simulation, must go through possible solutions one by one, like testing every single key on a keychain until you find the one that fits. This process is painfully slow. For example, cracking a 1024-bit RSA encryption could take a classical computer thousands of years. But a quantum computer can leverage superposition to try all possibilities at once. And then, with the help of quantum algorithms such as Shor's or Grover's, it can directly pinpoint the optimal solution, like trying all the keys simultaneously and instantly finding the right one. This makes the process exponentially faster. That same 1024-bit RSA encryption that would take millennia for a classical machine might only take a quantum computer a few minutes. In short, a classical computer is like a step-by-step calculator, while a quantum computer is like a magician that exists in all possible places at once. Their core difference comes down to whether they can harness quantum superposition to achieve exponential parallel processing. But superposition alone isn't enough. The true breakthrough comes from quantum entanglement, a mysterious connection that links qubits together, turning them from isolated players into a tightly coordinated team. So, what is quantum entanglement? It describes the spooky action at a distance between 2 or more quantum particles. Once entangled, their states are linked, no matter how far apart they are. Change one, and the other instantly reflects that change. Imagine quantum twins. One goes to Mars, the other stays on Earth. The moment you measure one twin as spin up, the other instantly becomes spin down, even across millions of kilometers. In physics terms, entangled particles can't be described separately. They form a single, inseparable system. Because of entanglement, qubits can form a global, correlated state, the foundation for quantum algorithms' exponential speedup. Take 2 entangled qubits, for instance. They don't just have their own separate superpositions, like qubit 1 is 0 or 1, and qubit 2 is 0 or 1. Instead, they form an entangled superposition of all 4 states at once, with probabilities linked together. This allows quantum computers to process all 2 to the power of n states simultaneously as a single whole, rather than separately. So what can quantum computers actually do? They unlock speedups for problems that are basically impossible on classical machines. Take Shor's algorithm, which can crack RSA encryption. Its key step is period finding, where entangled qubits hold all possible period information at once. Then, through a quantum Fourier transform, the correct period is extracted. Without entanglement, this global correlation wouldn't exist, and the algorithm wouldn't work. Or Grover's algorithm, which speeds up searches to square root time, a huge leap compared to classical brute force. Another major application is quantum simulation. Since molecules are themselves quantum systems full of entanglement, simulating them on classical computers requires crude approximations. But quantum computers, by harnessing entangled qubits, can natively reproduce molecular behavior, opening doors for breakthroughs in drug discovery and materials science. Of course, there's a big catch. Qubits are incredibly fragile. They suffer from decoherence, one of the toughest challenges in quantum computing. Decoherence happens when the quantum system interacts with its environment, like stray air molecules, weak electromagnetic radiation, tiny temperature fluctuations, or even the act of measurement itself. These interactions act like noise, breaking superpositions and tearing apart entanglement, collapsing quantum states back into boring classical 0 and 1. If decoherence happens mid-calculation, the exponential advantage of quantum computing instantly disappears. For example, 50 entangled qubits could represent a quadrillion states at once, but if they decohere halfway through, they collapse into just 50 classical bits, no more powerful than an ordinary laptop. And decoherence happens fast. Even in near-perfect lab conditions such as ultra-low temperatures, high vacuum, qubits might only remain coherent for microseconds to seconds. Complex quantum algorithms need much longer runtimes, which means error correction is absolutely necessary. A simple way to picture decoherence is to think of it like a drop of ink in water. At first, when the ink drop enters still water, it remains a distinct whole. This is like quantum entanglement, where everything is connected as a single system. As the ink starts to spread out, it can take on many possible shapes, similar to a quantum superposition with multiple possibilities coexisting. But as time goes on, the ink molecules collide with water molecules, just like a quantum system constantly interacting with its surrounding environment. Eventually, the ink disperses completely and blends evenly into the water. At this point, the original drop is gone forever. This is decoherence. The quantum state, once rich with superposition and entanglement, collapses into a definite classical state. And just like the ink can never reform into its original drop, the lost quantum properties cannot be recovered. In other words, decoherence is the process of quantum weirdness fading into ordinary reality. This is why quantum computers, while impressive in theory, are still far from mainstream reality. To fight decoherence, different qubit technologies require extreme environments. Superconducting qubits need temperatures close to absolute zero, minus 273.15 degrees Celsius. Ion-trapped qubits require ultra-high vacuum chambers. Photon-based qubits need shielding from stray electromagnetic radiation. These conditions make building and maintaining quantum computers incredibly expensive and complicated. Right now, they mostly exist as experimental research platforms. Scientists are working on quantum error correction and advanced control techniques to extend coherence times. But achieving large-scale, stable, practical quantum computers is still a long journey ahead. And that's all for today's video. If you enjoyed this deep dive into the science behind quantum computing, don't forget to like, subscribe, and hit the notification bell. See you in the next one.